So a friend of mine who's in fact in cybersecurity for automotive had his car stolen.
That's ironic.
That's very ironic. I thought it was like a trophy hack from some guy that was just going to like leave it around the corner or something. But no, it was stolen purely by the odds. In fact, his neighbours had a car stolen the same night. So in that case, that was a CAN injection attack, and he's been trying to track down how the hell they did it.
Hello, everyone, and welcome to the Altium On Track podcast. I'm your host, Zach Peterson. Today, we're talking with Ken Tindell, CTO of Canis Labs. I've been seeing Ken Tindell post quite a bit about CAN bus on LinkedIn lately, and I have done a little bit of research and realized that this guy is quite the expert on CAN bus, specifically in the automotive industry. So I'm very happy to be talking with him today. Ken, thank you so much for joining us.
Good to be here.
Yeah, so maybe since you're a new guest on the podcast, give us a sense of your background and how you got started at Canis Labs and how you became, I guess, such a guru on CAN bus.
Yeah, I started a long time ago in the automotive industry. So my PhD was in real-time scheduling theory, where you have to guarantee everything runs on time. And this was in the mid-90s. And back then, the car industry was just moving over to CAN bus. And they had a problem with making sure that everything on the CAN bus runs on time. And so Volvo started a project with me. And I started a company to support that project. And that's how I got started in CAN bus. That company was later sold to Bosch. And then I started Canis Labs to focus on CAN security because back in the 90s, the internet was still dial-up and no one had any concept of hacking your car from the internet, and things are a bit different now. So that's the new focus.
Yeah, back in the 90s, hacking, I think, was more associated with a movie, Hackers, and not something that companies have to deal with on a daily basis.
Yeah, exactly.
So you're really a hardware security firm or a hardware cybersecurity firm, it sounds like.
Yeah, well, it started in embedded software because that's what we focused on in the early days of CAN, because we worked with the silicon vendors in the very first CAN controllers that came out, and we focused initially on a security gateway that copies CAN frames from an unsecure side to a secure side, kind of like a firewall for CAN frames, and pretty soon we found that the best way to address security is actually in hardware itself, to try and lock down the ECU that's been compromised in some way and prevent attacks going on.
So you said you worked with silicon vendors. You were providing IP?
Actually, it was how to get the CAN controllers operating according to real-time requirements. So in the very first CAN controllers didn't really handle the buffering on the CAN controller properly. So you'd get a thing called priority inversion, where a high priority urgent frame gets stuck behind a low priority frame in the buffer, and then there's a whole bunch of medium priority stuff on the bus that delays the most urgent thing. So everything starts to fall apart for timing, and that's the thing that CAN needs to do right. So we worked with what was then Motorola on designing the MS CAN. It was the first CAN controller that did all the buffer scheduling correctly, and ever since then, every small CAN controller has used the same buffering scheme that we designed for Motorola. So it was less hardware IP and more just the intellectual rather than the P.
I see. So this is more a design solution for them to implement in their own hardware.
Yeah, exactly. So they produced the world's first properly real-time compliant CAN controller, and then everyone else kind of copied that design afterwards.
So, I mean, CAN bus has been around for a long time. I know it's decades old.
I think it was launched,
87. So it's early in the morning for me, so I'm slow on the math. That's 36 years.
Yeah, nearly 4 decades. That's right.
That's a long time for a protocol to still be the dominant protocol, I would think. I mean, I'm having trouble.
Ethernet's
Ethernet. Ethernet's older, sure, but I mean, at least the speed is advanced on Ethernet.
Yeah, I mean, there's things that with CAN that's the speeds advancing. So the latest stuff in CAN is CAN XL that goes up to 10 megabits. So yeah, the CAN's not stood still. There's all kinds of stuff going on there. And anyway, in real time control systems, it's not about bandwidth; it's about latency. And if you have a 100 megabit network, it's 100 times faster than the fastest CAN network. CAN still has really short latencies that can't be beaten, because the time taken to get an urgent message on the bus, because of the way it prioritizes it, it jumps ahead of anything that sort of round robin or time division access can provide. And then if you look at some of the Ethernet architectures with multiple switches, you've got hop, 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 hop. And it struggles to hit those kind of constraints that CAN can meet. So, and CAN is extraordinarily cheap to implement. So the wires are very low cost, and in silicon terms, you're talking a few thousand gates for a CAN controller. This comes on devices virtually for free at the current silicon sizes.
So everybody, at least recently, has been talking automotive Ethernet. And then for some applications in the vehicle, replacing copper with wireless. So probably the most common one was like the battery management system for electric vehicles.
Yeah.
Making it a wireless BMS.
So I looked at battery management wireless some time ago to see if it was possible to do a wireless kind of version of CAN that has those latencies, because with battery control, if things start to run away, you need to be very, very quick in getting control over that. The trouble is wireless. It has some major advantages. Partly not having to get connected to 800 volts of a stack of batteries,
right?
Is a major win there. But I've seen other techniques that basically hop from cell to cell with inductive coupling or magnetic coupling on the physical layer. So you can hop across all of the cells, and you don't have that kind of problem. But I mean, that's not my area. But yeah, wireless is solving certain very specific problems there. Of course, it also has very specific security problems, because if someone can interfere with the wireless, or even worse, hack the wireless as the vehicle's driving along, you have a completely different set of problems on your hands.
Well, I bring that up because, and specifically automotive Ethernet, because that has received a reasonable amount of attention in the past as, a potential replacement, a high data rate replacement for CAN, maybe only in certain part of the vehicle. But as the industry focuses more on autonomous vehicles, there's a lot of data involved with all these different sensor suites, and you have to move it somewhere. And you need a high bandwidth protocol to do that.
Yeah.
So it seems to me that there's a little bit of a competition here between a more advanced protocol that has higher latency, even though it can deliver higher bandwidth, versus something like CAN, which is lower speed, but has the latency needed for real-time control over the automobile.
And that's why the designs they coexist, because if you're doing real-time control, it's not really about large amounts of data. It's 16 bits for a speed value, or 8 bits for a temperature value, and you're not sending large data. If you're dealing with cameras and stuff, then obviously that's completely inappropriate for CAN, and that's why Ethernet's coming in primarily is for the high bandwidth sensors like LiDAR, radar, cameras, many cameras, and you need a complete architecture for that. Mixing that up with the real-time control, particularly the safety critical control, is really a challenge. So one of the things that CAN does is it's got a property called atomic broadcast. So if you send a frame on CAN bus, it's guaranteed to have been delivered to every other online device on the CAN bus, because CAN doesn't just throw away a bad frame. It has a low level built into the hardware, retransmission. With Ethernet, you have a frame check sequence, the CRC, and if that's bad, you just throw the frame away. And then you leave it up to a higher layer of software to try and work out, did the frame get noisy on this one? Did that one get it and this one not get it? And trying to put the atomic properties of that, where you want everything in with a consensus view of a control variable, is really challenging on Ethernet. They were trying to do this at NASA in the 80s, And it's a massive challenge. And when you start to put all the latencies in place for software that says timeout, retransmit, acknowledge, did I get acknowledged from everybody? Do I do another round? Blah, blah, blah. Then you're really starting to lose all of that. And CAN delivers all of that built into the protocol. So for real-time control, it's a different field, and this is why you're seeing designs that are mixed. So there's Ethernet for high bandwidth, particularly with cameras. You can't send anything compressed because the artifacts really mess up the vision systems. So they have to go raw camera images. That's a heck of a lot of bandwidth. And then you're seeing CAN for real-time control, and then some gatewaying of data back and forth that is needed to be shared, speed values and stuff like that.
Well, with something like camera images or like a radar point cloud or LiDAR data, I mean, the architecture that I've seen usually come up is like some kind of central, processing computer in the vehicle somewhere.
Yep.
And then it connects to these sensors and they're streaming data off at, 10 gig Ethernet or higher. Probably I mean, I've worked on a system that's dual 28G. That's a lot of data and a lot of cameras and a lot of radars all at once. But it seems to me that the solution there, because you have a latency issue, is do all the processing on that sensor and then send out the results on a faster latency protocol.
Yeah, I mean, there's architectures for dealing with that, but that's not what most of the stuff on CAN is. It's things like the indicator light's on, or the door is open, or the locks are closed, or the temperature, the fan in the climate control is moving, and the left fan is open, and the right fan is off, and all of this kind of little tiny, they're basically little switches and tiny sensors. So it's a whole different class of problem. So you're dealing with much different amounts of data, different types of processing. So
I see.
They don't really clash, and that's why you're seeing this kind of hierarchy. So there's an Ethernet backbone for very, very fast data stuff, and then there is CAN for real-time control. And one of the other problems you have is the sensors and actuators are physically where they are in a car. A door is where a door is, and therefore a door lock is where the door is. And so these things are difficult to centralize. I mean, there is a general trend towards people wanting centralized domain controllers, let's call them, where you start to get rid of all these metal boxes of electronic control units and push them into a centralized computer, and then do much more in software, and then send end actuator commands back out across a real-time network. And so you've moved lots of the control algorithm into the center, and that's feasible, at least at the initial level, because lots of the control algorithms are actually models built from modeling tools like Simulink, and you could just take them out of ECU, push them into the center, and then do the control there. So you take the sensor readings across CAN or whatever into the algorithms, and then back out across the bus. But there's a whole bunch of problems with that that are technical and non-technical. So the non-technical ones are, you're now changing the whole supply chain from someone who makes an ECU with a mechatronic solution with the hardware, and now you're saying to give up their algorithms and hand them over as source code or something to somebody else who may be a competitor to do the integration. There's a huge problem there. And then when you're running on a central computer and your algorithm goes wrong, is it your fault? It might be someone else's algorithm ran for too long, and now meaning
the data that they
liabilities.
You mean the data that they gave you could? You mean the data that they gave you could have been incorrect, or the result?
No, it's more. Their software could have gone crazy and used a load of CPU time, and then you didn't get a look in because the scheduler couldn't fit you in, because their software ran too long. Because now you're on a shared CPU resource. So now you've got to worry about who else is on the same CPU. And then if they have a supply chain attack, so someone got some malware into their component, but it made your component fail, your software component fail, who's at fault now? And even if it's easy to answer that question, it's not easy to answer the question, prove it.
Oh, sure. Yeah, especially when the supply chain is not consolidated in a way that would enable that very clearly.
Exactly. Exactly. So the whole idea is you're taking suppliers that were delivering you mechatronic solutions, and now they're supposed to be delivering you little bit of tronics, and somebody else maybe is doing the software, or their software is being run in the environment. And now you've spread around the supply chain liabilities, and there's and clear lines of responsibility. So it's some challenges there. You can solve these, but it's not as plain sailing as drawing a square box on a PowerPoint diagram and then just saying software.
Well, I guess solving those types of problems and yet still having separate companies and separate structures that requires coming together in these kinds of partnerships to develop these systems.
Yeah, absolutely. And I've seen different silicon solutions. So I was at a show where one vendor was showing effectively you could virtualize ECUs because they had so many CPU cores and such strong partitioning and memory between them, and the internal arbitration between the AXI buses on their crossbar and stuff was done such that you could completely isolate these separate cores. And then you're dealing with a solution that if one core goes crazy, it can't disrupt somebody else's core, and at that level is you have like virtual electronic control units, and then that hardware solution is a way of addressing that problem. And yeah, you could throw hardware at this, and some people are looking to do that.
Very interesting. So going back to security for just a moment. So one of the main reasons I wanted to bring you on the show is because I do see you post a lot about CAN bus security, and I think we have this idea that sometimes when the protocol is lower level, maybe it's a slower protocol like CAN, at least in terms of the data rates. It is not going to be something that is worth hacking. That's not where the gold is. But I think that's totally wrong, and you've shown some examples of it. And we actually did a podcast with Joe Grand, who's well known as a hardware hacker, and he had mentioned some points about getting physical access to even these low level buses that could allow you to totally take over a system.
Yeah.
So what exactly do you do in the area of security, and maybe we can talk about what the implications are of that.
Yeah. So there's to be clear, there are two major types of attack on the CAN bus. One is when you have access, the bad guy has access to the physical wiring. And then the other is where the bad guy has access to the computer that has access to the wiring. You see what I mean? So, for example, if you have a tire pressure monitoring system, they talk to sensors over RF. I've seen hacking of basically spoofing those tire pressure things to cause a buffer overrun to get control of the ECU. So you could access the tire pressure ECU from outside the car by lying to it about the tire pressure data and spoofing it. And then you're on the CAN bus because you now have access to an ECU that's connected to the CAN bus.
So, I mean, what could you do with that? I mean, is this, we're going to pop the locks and start the engine?
Yep. Yeah, you could do that. Yep.
That's it.
Yeah, I mean, basically, the whole car is, and then there's not normally one CAN bus. There's normally several CAN buses, at least two, and then in higher end vehicles, 3, 4, 5, 6, 7, 8 different CAN buses. They're partitioned off because they run out of bandwidth and they need to run these buses in parallel. So if you get access to the powertrain side, then you can spoof CAN frames as if from any other ECU on the powertrain side. So you can do all the things that the powertrain system can do. So that's the gearbox, typically the brakes, the engine, often headlights and things like that are on powertrain because of physically where they are. So you could spoof anything.
So that's, speed up the vehicle to 100 miles an hour, slam on the brakes.
Yeah, so some of these systems, so it depends. So if there's a system called eGas, which is basically electronic throttle and no physical linkage to a plate on a spring that opens the air input to an engine, then you can race the engine, and if you have access to the gearbox, you could potentially move the gear. So for example, the gear shift is often on CAN, and when you're doing that, you're just activating a switch and it sends a frame to the gearbox to say please go into this gear, and then the whole gearbox powertrain system then accepts your commands or rejects it if it's too dangerous to shift gear and so on.
And here I am
So
shifting gears, thinking that I'm actually shifting actual gears.
yeah, no, not anymore. Certainly not on automatic gearboxes. I think even yeah, I mean all these clutchless systems. They're physical gearboxes, but the software is asked for the gear. So if you spoof those frames, you could you could put the car into a certain gear. You could race the engine. You could cut the engine off. Things like power assistance on the steering, the electrical power assistance. You could tighten up the steering so it's very hard to turn. You just disable it.
Wow.
There's all kinds of stuff that you could do. And then if you could get inside the ECU itself, for example, you could hop from one ECU to another by exploiting another buffer overflow and then jump into that ECU. You're accessed directly to the actuators. So no longer just responding to certain message requests, you're now directly controlling actuators. So you could do all kinds of stuff.
So when you say overflow the buffer, this is just bombarding with messages in a format that will trigger a system the way you want it to. I think that's
this is
little
classic.
vague.
There's nothing new about this. This is classic. How you hack embedded devices is the quickest way to do it is to pop the firmware out and then run it through the Ghidra tool that the NSA has published, which it's a reverse engineering tool, and it gives you kind of C that represents the code it's seen, and then you can run it over some tools, look for buffer overflow bugs, and then the kind of messages to craft to get it to fail. Or the kind of slow and simple approach is to bombard it with just random garbage and see if it crashes. And as soon as you get a crash, that something, the stack got corrupted or something, and then you start to hone in on exactly what caused that crash. I mean, that's how the tire pressure one was done, which you just produce garbage sensor values, and then it crashes, and you go, aha, and then you home in on what caused it to crash, and then you get a magic payload to take control of the ECU. But that's how all of this kind of hacking stuff works in a large part.
So for CAN bus, I mean, it is copper wire, and you would have to get physical access if you were going to jump directly onto the CAN bus. You have to get physical access somehow. How are people doing this? I mean, aside from just drilling a hole in the side of the car.
Yeah, so this is a wired access to the CAN bus, and you just need access to that twisted pair. You can cut it with a pair of wire cutters and splice in a little magic box, and then that magic box sends CAN frames on the bus. But also, because it's directly on the wires, it can start to screw around with the voltage levels and stuff to make it much harder for the system to respond to an attack. So the way you find the connectors is the wiring diagrams tell you where the wires are, and for the ECUs and what they do, and you say, right, I need access to the powertrain ECU. So for example, one of the cars we're looking at, the engine immobilizer ECUs on the powertrain side, so are the headlights. So you crack open the headlights and you pull the connector off the back, plug into that, and now you can directly send commands to the engine immobilizer saying, hey, I'm the key fob, and I say it's okay to drive. And it's like, okay.
Wow. Okay.
Yeah.
So basically any two devices or any two subsystems that are on the same bus, the one that's easiest to access physically, that's the one they go after, and then they can get access to every other device on the bus.
Yeah, so you can just send messages, and you just spoof it, and you lie and pretend you're the other one, and it just accepts your messages. So the headlight one's quite good, because once you physically move the headlight, you've done too much damage, and then you can put the connector back and everything and sell the car on. The ones where you punch a hole in the side of the door or in the side of the wheel arch or something, you've obviously got some damage there. So these things are sold very cheaply at export. They drive them away. They cut off any tracking antennas, they stick them in a shipping container, and then they ship them abroad, and they get bought for a small amount of money, and everyone's making money out of this except the insurance companies and the owners.
So when so you'd mentioned just a moment ago that they can figure this out from a wiring diagram. I mean, would this be like the wiring diagram from like a control from a repair manual?
Yeah. So if you look at the wiring diagram, they're all all the CAN buses labeled, and they normally got colors for CAN high and CAN low, and then twisted pair, and they label up the connectors, and they say this is on to pin number, because the mechanics have got to go in and repair these things. So
sure.
it's just it's so they know where the wires are going to work, and then they'll get stolen car, and then they'll have a hacking of an ECU in there to see if they can spoof it. And then once that information is known, they make a little tool that is about $10 BOM cost. And then on the dark web, you can sell that for $2,000, $3,000, $4,000. You see them sometimes on websites. So there's what do they call it? Safe. So what's it called? A backup keyless override device or something like that. And it's to basically avoid all the immobilizer stuff. And the one I've been looking at in a little JBL Bluetooth speaker thing about that big. So if you get stopped by the police, you say, "Hey, it's a Bluetooth speaker." And you just disguised it. Don't even go with some kit that they can see. So So what key for the attackers there is they have knowledge of the things. They've done reverse engineering, and they know how to package up an attack that seems sophisticated if you take a look at it. But these dumb thieves, they just buy a box that you press the play button and it deactivates the immobilizer and opens the doors.
That's incredible. I mean, I guess I shouldn't be surprised that as the technology in cars has advanced, the methods for stealing them or taking control of automobiles also have had to become more advanced. But I didn't think it would have gotten to the point where you can just go on the dark web and buy a little box that overrides a vehicle and lets you get in.
Yeah, I mean, we've been here before with keyless entry and relay attacks. They're quite famous now, and the manufacturers know about those much more. And that's a very sophisticated attack. You've got wireless antennas trying to power up a key that someone's left on by the door, and then the relay thing. So it's actually a very sophisticated attack in terms of the kit. But the thieves don't have any level of sophistication. They just wander around pointing an arrow until it gets a hit.
Wow.
So CAN injection is like the new relay attacks. And it's in many ways much easier to mount those attacks than the relay ones, particularly as manufacturers have started to respond with keys that go to sleep when they're not moved and things like that.
Interesting.
So that's the common technique for it now.
So you said the manufacturers know about the relay type of attack.
Yeah, that's quite common.
So are they aware of these CAN bus type of attacks? Varying degrees?
Well, it's a bit like when an ant crawls over your toe. Have you noticed the ant or is your toe? I mean, these are gigantic corporations, and the knowledge of this space is, not uniformly allocated around the company. So I am sure lots of the manufacturers know. There are people that know about these things, but is it common knowledge like it is for relay attacks? I don't think so. So a friend of mine who's in fact in cybersecurity for automotive had his car stolen.
That's ironic.
That's very ironic. I thought it was like a trophy hack from some guy that was just going to leave it around the corner or something. But no, it was stolen purely by the odds. In fact, his neighbors had a car stolen the same night. So, in that case, that was a CAN injection attack, and he's been trying to track down how the hell they did it. And the Times newspaper picked it up and ran the story, and the manufacturer's quote was like, "We recommend you put your keys in a metal box so they can't be used to steal your car." And it's like,
really, that's their solution. That's not
how it works. That's for a relay attack. So it was quite clear they're talking in this to the journalists. They're talking about a CAN injection, and it's just the same old spokesman stuff. So it's not culturally through the car companies yet, I think.
Wow. Okay. So what is the solution, at least on the system side or on the design side? Is there something that you add to the PCB? Is there silicon IP that has to get added into the chips that are being used in these different systems to then access the CAN bus?
Okay, so the first thing to point out is that a lot of these attacks on new cars, those new cars, they've been manufactured for 2 or 3 years now. They started life maybe 8 years ago. And 8 years ago, this sort of space was a very different world that we were looking at. So a lot of the security in those cars is not like they're doing at the moment. So one of the solutions to this is to have encryption and authentication of CAN frames. It's a bit of a pain to do it for all of them, but certain key ones to do with things like the immobilizer and the locks and stuff, you can put encryption codes, authentication codes inside the CAN frames, and then if you're trying to hack it, you can't spoof anything because you can't get the encryption codes because they're unique per vehicle, and so that won't work, and you just made a hole in the vehicle for no purpose.
So this wouldn't be a case of getting the firmware and being able to reverse engineer it and see this. This would be hard coded into the silicon.
No, so you can do it in software. In fact,
Okay.
my company, we've got a little security library that's about 2 kilobytes of code. It's really small. It uses AES and proper encryption. And as long as you burn different keys into different cars, so that all the keys are unique, there's no one canned hack box that they can get, and they need to get the keys out. Now, getting the keys out is not like getting at the wires. You've got to get into the ECU itself. You've got to take the ECU out. You've got to put it on a bench top, get a JTAG debugger or something on there, maybe one of these differential power attack things that look at the voltage power lines and can work out states of transistors and stuff. No thief's going to do that on the side of the road.
Right. They're trying to just get in, get the car, and then get gone. They're not going to take the time to actually extract an ECU, go back to the lab, spend a few days, and then come back and say, I'll steal this car now.
Yeah, exactly. So, I mean, you do have to be a little bit careful, because if you're not careful with the protocol for communications, because you need effectively a rolling code. And one of the new standards for encryption on CAN has a rolling code of just 8 bits. So you only need to see 8 frames, 256 frames, and you've seen all of the combos. And therefore, if you just captured them all, you could replay those messages back, and they'd look like they came from an authenticated device. So the model there, then the thief would attach something to the CAN bus, leave it. It would then listen to the key being unlocked. If you remember back in the old days with remote fobs, they would have radio receivers in car parks, and they'd listen to your car being locked or unlocked, and then they'd come back and then replay the radio signal. So it's similar. You could do that. So you have to get it. You have to be careful. But if you're sufficiently careful, you could do a firmware update of these ECUs, and then they wouldn't be stealable via this. The car wouldn't be stealable via this CAN mechanism. So that's, if you like, the wired street thief attack. But the other types of attack is where you break into the ECU itself. And encryption is less helpful there, because you can get the ECU to do the spoofing, and it's got access to its own keys and so on. And then it's much easier for it to exfiltrate those keys to you, or just spoof the messages you wanted anyway, because you've got the encryption keys in there. And then that's where you start to need to look at proper hardware solutions that lock away an ECU that's failed in some way and has been hacked. You need to make sure it can be cut off the bus and denied access to everything else. And there's a whole bunch of those techniques.
This is really interesting, because when something like the relay attack becomes common knowledge, suddenly all the car makers, it seems like, have come together and said, hey, this is how we stop this, and it's in our collective interests to stop this kind of attack. And now that everyone knows about it, there are things that can be done. But when we're talking about something like CAN bus attacks, I'm just wondering, what does it take for the automakers to do something? I don't even know what the something would be, but to do something. I mean, if you're talking about someone taking over a vehicle and then being able to control a vehicle to the point where they could even cause an accident, that seems like a lot of liability on the shoulders of automakers. Is it just a cost versus liability calculation?
I don't think it's as cynical as that. It's a very complicated space. So once you have access to, you hijack an ECU through a firmware bug, you can do a lot of things on the CAN bus, and because you have direct access to the 2 GPIO pins into the CAN transceiver, you don't even need to use the CAN controller that's on the chip. You can actually go underneath the CAN controller and then just bit bang those pins and screw with the CAN protocol itself. And I've got a hacking toolkit that's open source to prove some of these things. So you can do all kinds of stuff. And so defending against that is a different class of problem from just using encryption, because encryption is like a software layer above CAN. But if you can come in and start screwing around with the actual underlying protocol, yeah, yes, it's a different level of defenses you need to protect from an ECU that's gone bad. I mean, you shouldn't have an ECU bug, but I think we all accept that this kind of software has bugs in it that can be exploited and do awful things. So it's not just in the future, it's not just theft, it's also attacking vehicles for ransomware, for example. You can imagine a very large payoff. So, and hence a very strong incentive for someone to try and do that. I mean, I've seen some research on detonating airbags over CAN bus.
Really? Wow.
Yes, because it turns out that it's in fact it's a requirement in most countries to detonate all the airbags when you go to recycle the car, because they're little, well, they're like hand grenade detonators. They're little bombs in to inflate the airbags really quickly. And then you don't want your guy in a scrapyard having his arm taken off or his hand, lose a hand to one of these things as he's crushing the car. So they all must be deactivated. And the way you do that is you hook up a diagnostic tester thing in a workshop, and then you just go around, you air horn, everyone get out, and then you just detonate the airbags in sequence. But they were able to show that the kind of safety responses there of like the vehicle has to be stationary and you have to be in a diagnostic mode. The way it finds out whether that's really the case is it's looking at CAN bus to see what the vehicle speed is. And of course, you just lie and then send "I am a tester, honest" commands. So you lie to the airbag ECU and say that you're not moving, and the diagnostic tester is attached. And so yeah, if you were able to hijack an ECU, you could embed that inside the ECU itself, and then you're looking at all these different vectors in there. And to try and deal with that is a much more complicated picture than just encryption on the CAN bus. So the street theft, I think, is quite easy to solve, and lots of manufacturers in their current projects are already doing things like encryption on the CAN bus. What they really need to do, I think, is to put a firmware update out for everyone who's got the cars already that were made and designed some time ago. And that seems a bit unfair to leave people high and dry when you can fix it now, but you could fix it retrospectively because it's a software change. But yeah, how you address some of these wider issues on access to these actuators and things is a different matter. Yeah, it's a big issue.
So the companies, I guess the OEMs or whoever they've contracted out their designs to, the actual physical design of some of these modules where you could get access to the bus, are they designed with any level of physical layer protection built in? Or is that also an afterthought? Or is that an issue that adds cost and size and weight? And, obviously with vehicles, we would like to have weight lower, not higher, especially today's, energy efficiency focused world.
Yeah.
So are those kinds of things just not even a thought anymore? Or are they kind of pointless? Because if I can access 2 wires on a bus and get access that way, it doesn't matter what I do on the PCB or in the assembly, I can get access to the wires.
Well, it's both those things. So the wired one, I mean, fundamentally, it's extremely difficult if someone's got physical access to the car to stop a bunch of these attacks. But the one that's really scary is if you are cloud hosted and there's a telematics API that your phone uses. They didn't secure that endpoint, and now you can push 10,000 little malware deployment things over the infotainment or the telematics gateway or however it was done into ECUs all at the same time, and then detonate their airbags all at the same time, or just cut the engines or whatever, all at the same time. So if you were looking at nation state level of hacking, you can turn a fleet of cars into an area denial weapon, if you like.
Oh,
Just
Lord.
shut down all the highway network. So that's, if you like, that's the I won't say paranoid, but if you let your consequences of do your flowcharts of what could go wrong, that is at the maximum end of the appalling things that you could do if you did that. And so there's a very strong incentive for a bunch of well-funded groups to do that kind of thing. So the manufacturers have to respond, obviously, to that. And it's difficult because it crosses so many domains. So, cloud-based APIs to phone apps. I mean, who's an expert in that? And at the same time, CAN bus protocol hacking on the transceiver pins. I mean, it's a huge disparate area. and trying to wrestle with that whole domain is very, very difficult.
Yeah, it almost seems like you have to have people collaborating from across these different disciplines within a manufacturer and a third party, whoever is hosting that cloud endpoint to then, capture and process that data.
Yeah. Well, it's really difficult because, for example, you see, the OBD2 connector on cars is used, and you have these little dongles. The insurance company makes you put in there, and it monitors your driving style to then decide or charge per mile or charge, did you brake sharply a lot, and they'll charge you for that, which seems to me a stupidly bad idea. It's like, I just ran this person over because I didn't want to be charged $5 by braking sharply. It's a really bad idea. Anyway, the electronics in those and the firmware in those and the cloud services for those, nobody's really doing a proper control of that to say, because if someone got into the servers, which is not that difficult, particularly if they're not looking closely. I mean, you have to be top of the line internet, cloud hosting company to really have the expertise to handle that. And then there's firmware on the on the dongle ECU or dongle device, and it's it's got a little microcontroller in there, and someone's put the firmware together. You know how these things are built. They normally just go out and they grab the first thing that works and they glue it together, and it looks like it works, and they ship it. And in the case of these insurance company things, very often it's a white label thing. So it's like some company has got solutions, and then they badge it up for the different insurance companies.
Yeah, they just slap the insurance company's brand on it and call it a day.
Yeah. And ironically, the insurance company is unable to assess the risk for these things that they're putting into cars.
Yeah, talk about irony.
Yeah. And then the really bad part of it is there is no proper post forensics analysis going on in this. So you see a lot of crash analysis for the police looking, and each individual ECU very often has its own data capture around an accident or something, so that it can work out what the hell is going on and know if it's where the liabilities are not mine or mine. But trying to put all of that together in a big picture, it's actually very difficult for vehicle forensics guys to collect all that data and then build a proper picture. And if it's not being captured properly, so if, for example, this third-party dongle was plugged into OBD2 and it did something terrible on the CAN bus, how do you even prove that after an accident? No one was logging.
That's a great question.
On the bus. Sorry?
I said that's a great question. Yeah, how do you even prove any of that? I mean, forensic investigation is behind the times, I guess, when it comes to some of the stuff that could happen on a vehicle. I mean, it's one thing with looking at someone's PC, because you can get access to all the data on a PC, but cars are rolling computers these days. How do you get access to any of that? And none of that, it doesn't seem to me that any of that is really being logged anywhere unless there is a cloud connection to some third-party application. Yeah,
and then that would be a security weakness into the car from the other way. So
yeah, exactly. Yeah.
It's not easy. It's a very complicated, multi-dimensional problem here. Yeah. So, I mean, intrusion detection is one of the techniques that people are looking at. So, intrusion detection is like the CCTV of embedded security. It's like, well, we couldn't stop anything, but at least we could see what was happening, and there was these bunch of events and stuff. And so, we saw 3 attempts at breaking into the car through these techniques. We saw these kinds of things happening on the bus. We saw this, and then you capture that, store it. And then if it's a stolen vehicle, you recover it later maybe, and then somewhere, somehow, working out what they're doing has been captured, and then because otherwise all you know is your car just went missing, and you don't know how they did it. So intrusion detection is part of that forensics of like post-incident analysis, and there's some work going. I mean, there's work going in all of these areas, and it's just a very, very complicated problem. If you think about it, it's probably one of the most complex security domains that crosses from right down at the tiny wiring level and microcontrollers and firmware, all the way up to cloud-hosted services, and the whole shooting match is it has to be secure, and that's really a challenge.
Well, at least with access to the physical layer, where you're talking about injecting CAN frames onto a bus to try and overwhelm a device and cause it to crash, or to get it to read the frames that you want and act in a certain way. How can you, I guess through software or through hardware, find and sniff out those malicious frames and then prevent them from getting onto the bus? You had mentioned like a firewall technique earlier. What does that look like? Is that just a chip
Yeah,
that gets added onto the design, or is it something that gets implemented in the silicon?
yeah. So that's actually something I'm working on right now. Is a chip that, because you don't really want to do it in firmware inside an ECU that's got all this other stuff going on, because then you just basically broken the firewall. So it'd be really useful if it's an external chip that you fire stuff in and stuff comes out if it's allowed. And one of the things that we've been working on for a while is a technique we call it CAN HD. It's an augmentation for high speed and guarding the CAN bus, and it injects out of band data that sits in between the sample points in a CAN, because CAN is quite slow, like 2,000 nanoseconds between 2 microseconds between CAN sample points, and you can put a whole bunch of edges and bits in between some of those sample points under certain rules, and that lets you tag things like where physically the CAN frame came from. So if your data is coming out of your CAN controller that's on the microcontroller, and if it passes through, it can get tagged up with where it came from, and then a centralized, not just an IDS, intrusion detection, but intrusion detection prevention system can decode those tags in real time as they come past, and then know that frame came physically from where it shouldn't. So I'm the immobilizer key fob. Please deactivate. It's like, no, you're not. You are the infotainment system. So I'm not going to trust that. And in fact, I'm going to destroy that CAN frame before anyone gets to see it. And then I'm going to send a message back to the little tiny piece of silicon that's done that fingerprinting and say, switch this guy off because he's been compromised. Don't let it talk to the rest of the bus now. So that's what we worked on. In fact, I've got a little tiny prototype here.
Yeah, let's see it. Don't drop it.
So this,
there we go.
Yeah. So that's designed to to match the pin out of a fairly common CAN transceiver. So this is like an integrated security CAN transceiver. So on there is a little tiny FPGA with our hardware IP in there, a crystal, and a CAN transceiver, and a resistor, I think. And the little dots on the side are just a tear-off tab for the Tag Connect programming to probe. So once you've programmed the FPGA up, you can tear off the tag, and then that becomes like a multi-chip module that's a drop-in replacement on a PCB for what would be a fairly conventional CAN transceiver. So it kind of pretends to be a CAN transceiver, but it's got all the logic inside. That's actually probably the best place to do this. So NXP have a CAN transceiver called the Stinger, which has a very simple whitelist of CAN frames that you are allowed to send, and then if you send a CAN frame that's not on the list, it destroys the CAN frame. And if someone else on the bus sends a CAN frame that's on your list, then they must be trying to spoof you, and it destroys the CAN frame as well. So that's kind of a nice way of doing it. That doesn't work for wired attacks, because this whole destroying thing relies on the CAN dominant bit being able to pull down, because CAN floats to recessive, if you like, and then anyone can pull the line into the dominant state. And hackers can drive a recessive actively onto the wires because they've got physical access to the wires. So it doesn't work on some attacks, but it certainly will stop another ECU that's been hijacked from doing anything, because that hasn't got changed electronics to drive the bus recessive, like I said. So there are hardware solutions to this. You can put onto the PCB. That was designed as a drop-in retrofit, but the long term is actually built into the CAN controller logic itself. So that's just part of the CAN controller.
So a hardware solution like this, I'm sure if you scale up to mass production, right, obviously costs are going to go down. Are the OEMs receptive to that kind of solution? Just a little thing that they can throw on the PCB, it's easy to design around, and it carries very low cost and no weight.
Yeah, I see quite a lot of resistance to this. NXP, I think, are suffering the same reluctance to use a piece of hardware. And I think it's there's a dominant, and you see this across the whole tech industry. There's this dominant feeling that encryption is the way to solve a security problem, and all security problems are encryption, and encryption solves all security problems. And then once we do that, we don't have any security problems. And it's like it solves your authentication problem. But what it doesn't solve is your denial of service attack problem. So that for sure, you send these messages and they're all authenticated, but if they never get through, what happens then? One of the car projects I'm working on, the shift switch lever. In fact, it's a button press. You press to go into drive. That sends a CAN frame every so often to say, "Hey, I'm alive, I'm alive, I'm alive." And then if the gearbox controller doesn't hear from it for a period of time, it says it's bust. And the shift controls are a vital part of the car. And so the failure mode is to say, okay, so the car has had a catastrophic failure of some kind because this is a vital piece of kit, and we will slow the car down, applying the brakes if necessary until it's stopped. We'll put on the parking brake, and then the car won't be allowed to move again, and you have to call out roadside rescue. So if your goal was to screw up a car and make it stop itself alongside the road, all you have to do is just block those CAN frames from that heartbeat CAN frame, kill it as it comes onto the bus. And no matter what encryption you're doing, it's not going to solve that problem because the messages aren't getting through. So then you've brought that car to a halt. If your attack was on the basis of demanding ransom for stopping cars on highways and then ramping up the number of cars until eventually they pay up, it's a very effective technique. Yeah. So you do need these hardware security things, I think, to block those kinds of attacks. But we haven't seen those attacks yet. At least they haven't been made public. If those attacks have been going on, I mean, they're not the sort of attacks you would make public, are they? But
well, I mean, cybersecurity issues have, I don't want to say dominated the news, but there was a period of time where it seemed like there was a hack being reported on some news channel every week, and it was big name brands that everyone knows about. It's just that they keep making the news because they're places that retail consumers use or purchase from, and it was like the online account that everybody accesses and just expects to be perfectly secure. So it seems to me that anything involving hardware security just kind of gets swamped and is a back page story compared to Target lost 50 million customer data profiles to a hacker, something crazy like that, because those are actual news stories that happen.
Yeah, so I think there's a kind of an asymmetry on the attitude to proper hardware security, because the thing is that the hardware security is actually easier to do because with whenever you have encryption, a friend of mine said that if you an encryption basically if you have an encryption problem, if you have an encryption solution, you've just created a key distribution problem or a key management problem. So all these cars have to have unique keys. Ideally, they need to be changed to prevent certain kinds of things where you can over time work out what the keys are. So they have to be updated every service interval with new keys. And then somewhere, someone has to have a database that manages and looks after all the keys so that when the workshop plugs in a tester, it says, okay, that's serial number, blah, 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 VIN number, blah. Here are your keys. And then if you take a spare part and program it in, you've now got to program that with the keys for that vehicle. And if you take a spare part out of a vehicle, you've got to reprogram it to use it in another vehicle and da-da-da-da. And then somebody breaks into your central database because that's what happens in central databases. And then they exfiltrate the entire database, which would only be a few megabytes probably for all of the vehicles. And now all the keys are known because someone stole the key database, because someone left a USB stick containing it on a train or something. So you have lots and lots of secondary and tertiary problems with encryption. So it doesn't solve all the problems, and it's like you have to really, really get it right, and to manage all this stuff. I mean, you see people's Bitcoin wallets being stolen all the time. That's an encryption. Those keys are supposed to be looked after, and people don't. They stick it on a USB stick. So hardware security's got a very nice model of deployment. It's like it's physically there. I don't need to do anything. It's just there. It's part of the design, and then it works. And there's no need to change it, and USB sticks don't cause it any problems. So, but these are quite complicated issues to talk through in a very, very complicated space, and I think that's why these things don't get the focus they should.
Yeah, yeah. Well, we've only got a couple minutes left, but I think for just the final question, I'd ask you what's coming on the horizon for your company.
Yeah, so our focus at the moment is a secure CAN controller that actually has a whole bunch of these features for denial of service problems, saying you're not allowed to send that frame, you can't, or you are allowed to send that frame, but you can't send it that often. And then we'll have an external CAN controller, and because of that, nothing on the host can get access to the pins on the CAN transceiver. And then this really starts to push the security. So a little external CAN controller chip. It's a harder IP, and if we make that into an ASIC or a high volume chip, then we have a real solution for this security on CAN bus.
Very cool. Very cool. Well, hopefully, as some of these things develop, we could have you come back on the podcast and discuss all this with us.
Yeah.
Well, Ken, thank you so much for joining us. We've been talking with Ken Tindell, CTO of Canis Labs. To everyone that's out there watching, make sure to check out the show notes. We're going to have some great links there so that you can learn more about what Canis Labs does. And of course, make sure to subscribe to our YouTube channel. You'll be able to keep up with all episodes and tutorials as they come out. And last but not least, don't stop learning, stay on track, and we'll see you next time.